Hello everyone, I am Navghan Thapaleeya, a postgraduate student at CEPT University, currently enrolled in the Master's program in Construction Engineering and Management. This video is my portfolio presentation for Studio 2, part of the course Construction Project Execution Monitoring and Control. My student code is PCM24423. In the following slide, I will be sharing the key insights, learnings, and field-based observation I gathered during this studio. Now moving towards project brief. So this project is about turning the railway station into a modern, eco-friendly transport hub. It will connect regional railway, the metro, and the upcoming high-speed rail to make travel easier and more efficient. It also aims to improve the passenger experience and support the local economy. The project covers 125 acres and is estimated to cost 2,400 crores. It is being built under the EPC model and is expected to finish in 2027. Some main features include a smart ticketing system, the MMTH building, a concourse with shop, better railway tracks, and new parcel buildings. The main goal are to make travel safer and more comfortable, support business activity, ease traffic in the area, and bring in more revenue for Indian Railways while also caring for the environment. Now coming to the cost of quality deliverables. So we have done prevention cost, appraisal cost, and deviation cost, which includes the cost of rectification of non-conformities. So preventive cost was calculated at 32,09,393 rupees. A major portion of this went towards establishing a quality control lab and purchasing lab equipment to conduct various tests, which together comprise more than 91% of the total preventive expenditure. Other important costs included staff training, internal audits, and quality planning. These investments are aimed to proactively processing construction issues through proper quality control framework before the actual work begins. In contrast, the appraisal costs were 2.33 crores rupees, which is much higher than the preventive costs. It includes expenses related to ongoing inspection, in-process quality checks, and material testing. The contrast between preventing and appraisal cost indicates that the site follows a reactive quality strategy, placing greater emphasis on catching errors after they happen rather than preventing them. A more preventive focused strategy could reduce long-term cost and enhance execution quality. You can also see the entire process of rectifying a non-conformity from moment it is raised to its close. Now coming to the non-conformity. So the first observed non-conformity was honeycombing, which occurred due to poor compaction during concreting. The total rectification cost was 3,296 rupees, with the equipment rental being the largest contributor, followed by labor and material costs. This kind of error, while minor in appearance, can lead to reduced structural durability and must be addressed through better supervision and proper compaction techniques. The second non-conformity was bulging in the beam, caused by improper formwork and inconsistent concrete pouring. The rectification cost was 5,542 rupees. The breakdown includes material costs such as Nitobond, Forsok GP2, and Penit, as well as labor costs for mason and curing and final inspection charges. Avoiding such defects require not only better formwork design and execution but also consist supervision, compaction, and curing practices. Now moving towards the tools of quality. This deliverable includes a control chart, histogram, and an Ishikawa diagram for root cause analysis. To assess the control quality, I use control chart, particularly X bar and R bar chart, to monitor the 7 days compressive strength of M70 grade concrete. These tools help detect inconsistency in the production process and ensure that it stays within control limits, allowing timely intervention when needed. Here you can see the value of upper control limit and lower control limit which show in tables. Coming to the X bar chart. The X bar chart plotted average compressive strengths from multiple batches. All value remain within the upper and lower control limit, suggesting a stable and controlled process. This confirms that batching, mixing, and curing were executed consistently, meeting strength expectation. In R-bar chart, the R-bar chart, which shows the variation in sample sets, also indicated control. However, some batches, especially 3, 9, and 10 samples, show higher variability. These spikes suggest minor process deviation such as improper mixing and batching errors, which require tighter control in future observation. As per future operations, as per IS 456-2000, the target compressive strength value should remain within defined limits. All our tested values exceed the minimum requirement of 43 megapascal, confirming the strength and quality of M70 grade concrete used on site and validating the testing method. In this slide, you can see a fishbone diagram of a non-conformity, which is honeycombing, that identifies the main causes under 5M categories: unskilled workers, poor quality materials, faulty machinery like vibrators, incorrect measurement practices, and improper construction methods. These are the major causes which we highlighted. These problem are these problems can lead to serious effects such as weak structure, poor bonding with reinforcement, inspection delay, and higher maintenance needs. To prevent this, some preventive measures are suggested like improving formwork, ensuring proper compaction and vibration, using good materials, and placing cover blocks correctly. Now moving toward the histogram. So in histogram, we consider free flow test of M70 grade concrete. Alongside strength testing, they conducted free flow tests of every transit mixer delivering M70 concrete. Result mostly ranged between 610 to 620 mm, which falls within acceptable workability limits. This is crucial to ensure proper flow during placement, especially in complex elements like ramps and high columns. This slide presents a work sampling study carried out over 2 days at the site. The main activity observed were slab concreting, slab reinforcement, column reinforcement, and shuttering near lip shaft area. The slide includes tour plans showing the location of each activity and spaghetti diagram mapping the movement paths of the site of a member on both days. This path helps visualize the time spent moving between tasks. The goal was to classify work as value added, non-value added, and necessary but non-value added to identify inefficiencies and improve work planning and productivity. Here pie charts show the number of observation and the percentage of each type of activity. First is value added activity. Value added means useful and productive work. Then non-value added but necessary activity. It means support work that is needed but doesn't directly add any value. Then third one is non-value-added activity. It means wasteful or avoidable delays. This chart helps to us to understand how time was used and where improvements can be made. First is slab casting. So slab casting has only 45% value-added work. The rest was NVA and NV. Major issue were workers waiting for concrete delayed during pouring and slow setup of concrete pump and concrete pipe. So better planning and smoother workflow could improve this a lot. Second, shuttering near the lift shaft at 51% VA, 28% NVA and 20% NVA. These show a lot of waste time. Delay were caused by late material delivery, unclear instruction from supervisor, and missing layout marking. Third one is slab reinforcement. So slab reinforcements perform very well with 81% of activities being value added, only 13% NVA and 6% NVA activities. This means the teamwork efficiency efficiently thanks to good planning, proper instruction, and materials being ready on time. Fourth one is column reinforcement. So column reinforcement had 55% value added, 29% non-value added but necessary, and 60% non-value added activity. While this is okay, there is still room to improve. The delays were mostly due to confusion in drawing and lack of coordination. This slide shows the activity-based work sampling analysis for day 2, focusing on four main construction activities: slab casting, shuttering near the left shaft, slab reinforcement, and column reinforcement. Each pie chart breaks down how time was spent, whether added value was necessary but non-value added, or was purely non-value added. First is slab casting. Slab casting at 56% of labor time is productive, but 29 was wasted, indicating room for improvement. Second was is shuttering near the lift shaft. So shuttering near the lift shaft at 51% productive work, but a high 28% of time was wasted. Then third one is slab reinforcement. So slab reinforcement was the most efficient with 81% of work being value added and very little waste. Fourth one is column reinforcement at 55% value added work, but a notable 45% was taken up by NVA and NVA tasks. This slide present an analysis of how time was spent and how frequently different type of activity occurred on day 1 and day 2. In the first 2 hours of day 1, most time was spent on setting up of the site like material safety, with less productive work, but later value-added work increased, showing better efficiency. On day 2, value-added work was already higher in the first 2 hours, meaning the setup was smoother and work started more efficiently. Overall, day 2 had more value-added activity and fewer delays. The frequency chart shows that most productive work happened during peak hours, especially from 9:30 am to 12:30 pm, and again from 2:30 pm to 6:30 pm. Work stayed consistent even in the evening, especially after 7 pm due to ongoing night work. The comparison chart at the bottom shows the day 2 had more value-added activity and less waste, meaning the team worked better and more efficiently than on day 1. Now moving towards the conclusion side. So this slide summarizes three key conclusions for the project. First, the cost of quality shows that more money was spent on inspection, means appraisal, than on preventing defects, which led to extra repair costs due to issues like honeycombing and pure foam work. Increasing spending on training and planning could help avoid this problem. Second, under tools of quality, the concrete use had good strength, but some defects were noticed due to poor practices, poor training, testing, and using quality tools like histogram and control chart can improve reliability and reduce future issues. Lastly, work sampling showed that productivity improved on day 2 compared to day 1 with better planning and fewer delays. More value-added activity were completed, especially after lunch and into the evening. This shows how preparation and clear communication can improve daily work performance. Thank you.